So, good afternoon. I'm just happy I'm not on after lunch, right? Because then you'd all be sleeping within 5 minutes into this presentation. So let me just give you a little background. Again, my name is Ezriel. I work for a company called Circle Software. We used to be affiliated with Circle here in the UK. We were the US branch, and so we still do a fair bit of education in the areas of Cics and DB2 and MQ. Through RSM here in the UK, but in the US we're Circle, and we also do all the IBM education and so on. And this section came about, to be honest, because we teach a 2-week internals class. You may or may not have been to a 2-week internals class. I don't know if you'd be happy to go to a 2-week internals class, but this is sort of a little bit of, you did, right? Yeah. This is a little bit of the overview from the internals class to just give you a feel for the internal structure of CICS, because although it's not really an art that's looked upon as proudly as it was, let's say 10 or 15 years ago, it is still a very valuable skill. In fact, probably the most valuable skill you can get is to learn internals, because once you know how the inner workings are, you can solve just about any problems that occur within Cics, right? And so I'll talk a little bit about that, but I built this as part one, by the way, of a 4-part session, so you're welcome to any of the other ones as well. In Share in the US, on the Sunday now they do a day's worth of education, and so we do a Cics immersion session that includes this as the starting session. So that's just a little history of why I built this introduction, right? But what I normally cover in this section is I go through the Cics structure. I'll tell you a little bit about the history of Cics going back to 1969, how it was structured, and the way it works today. So IBM's done quite a bit of work on CICS internally to make it function as fast as it does and as efficient as it does, right? So we'll talk a little bit about the domains and what a domain is and what does it mean. And then I'll go through some of the specifics about domains. For example, encapsulation is the key idea. I'll show you what that means. We'll go through these things called specific, generic, and callback gates and show you a little bit about the domain format. And then, by the way, I will tell you where you can find this information if you're a Cics person inside of a system dump. It's the easiest way to get to this information simply because I don't know what tooling you have. But if you can take a dump in CICS, which we all know we can, you can go in and verify the information that I'm giving you is actually correct. And a lot of this is available in a diagnosis reference, right? Have you ever looked at diagnosis reference, anyone? Okay, there's Al, he's done it, right? Today it's a 2,000-page manual. Yeah, no, it is. I mean, you wouldn't read it cover to cover unless you were insane. But you could pick out little sections and read about it. It's just much more easier to look internally, and I'll teach you how to learn how this stuff changes, because from release to release to release, IBM just changes stuff. So I'll try and give you approximate release numbers as best as my old memory can work, right? But then we'll talk a little bit about kernel linkage and how data is passed between programs. But this is not application programs. This is under the covers, how the system passes information to itself. Now, why is that of any importance? Well, if something fails within Cics, you get a message, and that message is produced from one of these individual domains. So I'm going to show you that. Then I picked out a couple of core subjects that are important to you, right? So a task versus a transaction. If you've been in Cics for a while, you understand the differences. Don't worry, you will after I go through it. And then I go through the real main domains: kernel, dispatcher, transaction manager, and AP domain. Notice I skipped storage, but I'll come back to that in a second. Those 4 domains are core to any task running in the system. And in my years of debugging applications, one of the things I will tell you is if you don't find footprints of a task or transaction within one of those 4 domains, it isn't in your system. That's the idea. It may be in all 4, which is what it's supposed to be in, right? And I'll show you how that works. But on occasion, for example, if you get a storage violation, you might only find footprints in 1 of the 4 or 2 of the 4, which means it's in your system, but CICS has cleaned stuff up and then found a problem. And so once you get an idea of where to look, you can solve a lot of the problems yourself. Now, how many people solve problems in Cics here? So if you do, you're probably familiar with, I'll take a quick look, and then if I'm not happy, I'll ship it off to IBM. Now, one of the reasons why we still teach internals, we also teach internals to level 2 in Raleigh, is because they if you look at the way things go in the world, they used to have a massive staff. Now they have a smaller staff. And the staff is quite a bit younger, and a lot of the older, more experienced people have retired. If you've ever reported a problem to IBM and found yourself waiting a week or 2 or 3 for a response, you realize that if you can help yourself a little bit, then you don't necessarily need them unless it's truly a Cics problem. So that's why we still kind of teach this. Now, I go through Storage Manager a little bit because Storage Manager is one of the areas that's changing within Cics, right? A lot of stuff is moving above the bar, which means we have more room to run applications below the bar in 31-bit storage. So a Cics region can now run a lot more work than it used to. And in America, in certain companies that I go to, I'm actually reducing the number of regions that they're running in a lot of cases because I can just pump the throughput through one region. If you actually put more work into a region, he's happy. It's really strange. So I'll talk a little bit about that and the 64-bit support, and then any questions you might have, we'll go through. So let's start with the Cics structure. So just over time, Cics was obviously created somewhere in 1969, around August timeframe. I guess we're coming up on the 50th year anniversary, but it doesn't mean that we haven't done any work with it. Anyone know how old Java is? Or Windows, right? I mean, we always talk about the mainframe products as being 50 years old, but Java, I think, is 30 years old, right? So when you think about it, all software products are old. It doesn't mean they're bad. It just means they've been around for a while and they've been debugged, which is what makes them actually better. Now, somewhere around the 80s, and I hate to admit I was there in the late 80s, IBM decided to restructure CICS. So let's talk about how it looked. There were a bunch of different areas of the product. They had programs, they had control blocks, right? And basically it was a big mishmash. Which would happen is, you know, my favorite example to give out in an internals class is if you go through program compression, why would you compress out programs? Because Cics only has X amount of space. And when he kind of runs out because you've loaded a bunch of stuff and you're running a bunch of transactions, we need to reclaim space. The way we do that is we throw out programs that are not being used. And in the old days, what would happen is if you hit program compression, IBM threw out every single program. They later learned that wasn't wise because what's the very next thing you have to do? Start loading back programs. So now they have a whole complex algorithm for figuring out what they should throw away. But back then, they used to throw out everything. And so you had these management modules. You had storage control program and program control program. They had their own control blocks. Storage control program, program control program used the PPT, right? Processing program table. You've probably done CETA defines. That's the program definition that you're making, right? And in Storage Manager, you'd also have control block. I'm going to leave that out for now. The point is that those programs could modify each other's control blocks, which is exactly what they would do in case of a program compression. See, if a program was in use, you couldn't throw it away. So what you do is you mark a bit in the PPT, and then when storage control would get control, and eventually that program would become unused, we could throw it out later on. But that allowed a program in one area to modify a control block that belonged to another area. That was fine until CICS 1721 days. I don't know if you've ever installed that far back, but if you remember back to 211, it took people several years to put it in. There were all kinds of temp storage problems and other things. Because if the if the management module developers were modifying each other's control blocks without telling each other, and suddenly the guy decided, I'm going to move this field, what do you think happens? The whole thing blows up. And so IBM said, enough is enough, and they decided to restructure Cics. And what they used to restructure Cics is this concept of domain architecture. This was actually invented here in the UK. It came out of Oxford University. It was a concept called Z back then. And the idea was very simple. It's object-oriented programming in the very, very early days. It was 1980s, right? Concept is simple. We're going to build a structural area. We'll call it a domain. Everything associated with that domain will live in that structural area. One structural area of Cics cannot touch another structural area of Cics, right? And if you look at this page and you go from here up, they started with 16 general purpose domains. And the idea, as we're going to see in a minute, is encapsulation. Encapsulation basically means if this domain needs something that this domain has, and you're saying, why would one domain need something from another? Well, let's pick one that we could figure out. Let's pick storage manager. Everybody needs storage, right? If everybody needs storage, that means that somebody has to ask him for storage. Actually, all these guys have to ask him for storage. But now we can't touch his control blocks. So we have to build an architected infrastructure to allow one domain to call another legally, but everything within that domain is encapsulated. Nobody can touch it. They can change the internal structure. They can modify the programs, and they don't have to tell anyone about it. Because if they build an architected way of communicating, and as long as that still works, we don't care what the internals look like, correct? However, when you're trying to debug something, you kind of have to know how it looks under the covers, because it's going to fall apart. So anyway, they invented this thing called domains. And what we did here on this page is actually quite interesting, because it shows you over the years of development. So this was somewhere around Cics ESA 3.1. I would guess it was late 80s, early 90s when it came out. And then what we're showing you here is version release modification internally was 3.1. And then they added a bunch in 4.1. They added a bunch in 5.1. They added a bunch in 5.3, and so on and so forth. Now we're using the internal version release modification. Once we went to transaction server, you might have noticed transaction server is 1.1, but internally it was 5.1, right? So that's kind of what we did underneath the covers. And today, the release that you might want to go to is CICS 5.4, which internally is 7.1. I guess they thought they were running out of numbers or something, so they used a different number internally than externally, or at least that's the excuse I've been given by a few people, but I can't verify that. Now, if you actually look at this, it shows you when functions came out, which is quite interesting. For example, just to take you through an area that I went through in quite a bit. So if you look at CICS version 1.3, right, we're at 5.4. If we look at 1.3, which internally was 5.3, you could see that over here they added the business application domain, the event manager, and the scheduler. These three domains work together to support BTS, Business Transaction Services. I doubt any of you are using BTS, but if you were using BTS, those are the domains you'd go through. If you're not using BTS, you never have to worry about them. So it's not like you have to learn everything that's sitting here, but nonetheless, that supports BTS. RX, just as an example, resource recovery, right? So this was back when you could actually run a batch job with two-phase commit protocol into a CICS region, right? It uses RRS or RMS, right? Resource Recoverable Management System within ZOS, and you could actually have a batch job communicate with Cics, and then when Cics returns the response, if the batch job completes, then the Cics transaction will complete. If the batch job fails, then we can append the Cics transaction and force back out. So that was a function they added in 5.3. And then the big one is right here, sockets, web, and document. That was a big turning point for the world of Cics. I was worried before that came out because we were kind of missing the big world. In 4.1, we actually added a little bit of web support, just a tiny bit. But in CICS 1.3, we made it part of the infrastructure of Cics. And so that was back when you got web support, CICS web support, which if you guys remember is part of the early days of web services, right? And so today, that's fundamental to the way we do things, right? If you take a look in the last 5 or 10 years, what's the biggest thing happening in Cics? Everybody's running web services. Everybody's mining data from CICS. So that came out back in CICS 1.3. And you can see some Java enhancements down here. And don't worry, I have a couple of pages that give you a one-line description of each of these domains. Now, one of the things about these page that you might not recognize here is these are all numbered generally. I don't have the numbers on this page, unfortunately, but domains have a number, right? The number is important if you're looking at the internals, but more importantly, they all have 2-character codes. Temp storage is TS. Why is that important? Wait a couple of pages and you'll understand. Once you remember these 2 characters, you know everything you need to know to get more information about this particular domain. So you don't have to memorize them, just remember you got it on page 1, right? Okay, so again, organized into domains. Each domain is a single major component of Cics, and the only exception is the AP domain. So if you go back to CICS, when it first came out, 3.1, 16 general purpose domains, we estimate back then 80% of the code ran in the AP domain. 16 domains, 80% of the code, all in the AP domain. Well, when you actually look at Cics, they had the restructure or new Cics, and then they had old Cics. Old Cics is the AP domain. Everything running within the AP domain is still running the way it did 40 years ago. Yeah? So the architecture internally is a lot easier to work with, right? Because they're not dealing with encapsulation. And in fact, you might say to yourself, well, over the years, as you see all the other domains, they've been carving code out of the AP domain. So today there's a lot less code that runs in the AP domain, but there's still a large percentage of Cics that runs there. As a matter of fact, if you look from release to release, if you have multiple releases of Cics, and you take a look at the modules that run within the AP domain, you'll find that what IBM does generally when they're playing with a concept is they will actually put it in the AP domain first. See if anybody likes it. See if, it catches on. And if it does, they'll build it into a separate domain. And that's why one of the things I should point out is you'll notice going all the way from CICS 5.1 to 5.4, there were no new domains, right? Because functionality, what did they add in the last couple of releases? They did a lot of functional improvements internally. The speed of Cics is a lot faster, and I'll explain why in a couple of pages. But the other thing is the function they added was mostly Java and other things. So they added it to existing domains that they came out with earlier. So they didn't need to create a new functional area of Cics, right? Okay, now, a couple of rules. Domains never communicate with each other directly, sort of. IBM will break the rules for speed. So I will tell you there are occasions where domains under the covers will communicate with each other because it's just a faster way of doing things. But nonetheless, the rule does still apply. In order for one domain to talk to another, we're going to figure out how they do that. So you can see also all calls are routed through the kernel. That makes the kernel one of the most important domains in Cics. Because if you want to know where somebody is within an application, the kernel always knows. Right? Because every call you make, if AP domain needs a bit of storage, somehow AP has to call storage, which we'll see in a minute. But before it gets from AP to storage, it goes through the kernel. So the kernel has a trace or a footprint of everywhere you've been, which means for program checks, appends, loops, the kernel's a great place to start, as we're going to see. Okay, so I've given you a list with a brief description of every domain. What I want to show you here is, again, the asynchronous domain is new because that's new function they added in CICS 5.4. And then some of the other ones, right, there's your dispatcher, the dump domain. You might know a couple of these. A couple of changes. Remember there was a local catalog and there's a global catalog? Well, the domain footprints still exist, but there really is only one, right? There's just a catalog today. So there's no separation as of 5.1 of the local and global catalog. That's a change that they made. They never told anyone. The domain anchors still exist. It's the way it looks today. The other thing is they've removed some domains over the years. IIOP, Internet Inter-Org Protocol, people don't use it anymore. It's been replaced, Liberty and all the rest of it. So they've removed the ability to do Corba object requests. Nobody seems to be crying, but that's the way it is. So I wanted to show you all these. Markup language, right? So this processes XML, and today it does a little bit if you have Java in there, and you can do RESTful API. Managed platforms for applications, platforms, and policies. So as you read through what these different things mean, you'll actually find that they apply to different areas of Cics that you've heard about. So I wanted to give you a complete list. I didn't want to go through it line by line because you'd just leave. So, okay. So now let's talk about what a domain actually really is. So all domains have an anchor block. For the old timers in Cics, do you remember what the whole anchor block was? What was the main control block in Cics? Correct, thank you, Al. So the CSA, the common system area within Cics, was the anchor for all of Cics. If you could get to that control block, you could get to anywhere else in Cics. Great idea. CSA, by the way, is alive and well. Remember, you have a little mini old Cics running in new Cics. That's the AP domain. So what is the anchor block for the AP domain? The CSA. It's a shadow of itself, right? It's much smaller, but nonetheless, it's alive and well. What IBM decided was what we're going to do is make sure every domain has an anchor block. And that says if I want to get to any control block within a particular domain, I should be able to get to it from the anchor block. Now, we're going to learn in just a second, but I'll tell you anyway, is the kernel is now the main anchor block for this system. The kernel within a CICS system dump, for your guys' knowledge, is always at offset hex 7000. Okay? So if you actually go to offset hex 7000 in a system dump, you'll see a 2-byte length indicator, a greater than sign, then DFH KCB, right? Kernel control block. That's the name of the control block. Now, within the kernel control block, there's something called a domain gate table. That domain gate table is just a bunch of rows, and each row represents a different domain. The row sizes have changed over the different releases. I'll talk about that today. They're hex 800 in length. And what it means is that offset hex 10 into that table is the anchor block for each domain as you go down the rows. Yeah? You just have to know what the order of the rows are. But even if you don't know, you go to that table, which is printed in a system dump. So if you use a formatted IPCS dump, right, and you ask for k equal 2, and you take a look at the kernel area, you'll see domain gate table, and it'll show you the rows. Offset hex 10 into those rows are the address of each of the anchors. And from those anchors, you can get to all the control blocks. Now, IBM doesn't print all the control blocks anymore, right? I don't know why. I guess they don't want us mucking with it or whatnot. But nonetheless, I'll show you some of the important ones as we go through that. Now, all domains handle their own recovery. They don't need anybody else. And most domains have something to allow for offline formatting. So IPCS, for example, is not even a Cics tool, right? It's a MVS or ZOS dump utility. And because Cics wrote an exit that runs in it, it can format a Cics dump. And it uses these offline utilities to kind of show you what's in a system dump. Now maybe I'll do a system dump presentation next. So let's talk about the calls. How does the whole thing work? Well, encapsulation is the concept, right? So each domain manages its own data and cannot access another domain's data. So what's in a domain? You got programs, you got control blocks, and then you have these domain gates, which are really just programs, but I'll show you what they are. These gates are how we call each other. So if I need a piece of storage, I'm going to issue a domain gate call. Now, to translate it into something that you can understand if you're looking at a Cics system dump, is you ever run trace? If you run trace, one of the things you'll notice inside of a piece of trace is that like the third column over, it says something like SMGF when you see a get main. SMGF is actually the program. If you stick a DFH on the front, because everything starts with DFH, the actual module you're invoking is DFH SMGF, and he's the guy who handles storage allocation below the bar. We'll show you there's some other ones, yeah? So I'm going to show you a little bit about it, but basically an entire domain is just made up of a bunch of programs. Depends on the domain. Most domains have at least 2, but some domains, like the AP domain, could have 47 programs, depending on the release. So Cics is not this huge product made up of millions of modules. It's actually fairly small and quite efficient. So, as an example, I threw up some domain gate calls here, right? So it's just an entry point into a domain, and that's what you see in trace. So each domain can have several gates. Each gate has a 4-character identifier. So let's talk about a few of them here. SMGF is storage manager, get main free main. That seems easy enough. So whenever you see SMGF in a trace, somebody's doing a get main. And if you read the rest of the trace, it will say, oh, get main, or it will say, I'm going to execute a get main, I just did it, right? And you'll see that the program that's involved is SMGF. Here's another one, SMAR. Storage Manager Acquire Release Storage. When a transaction starts up, did anyone notice that they tend to get storage, depending on the release, out of at least 4 subpools? They get it out of kick storage above and below the line. They get it out of user storage above and below the line. But who handles that? Well, every transaction that starts up, you will see SMAR run. And every transaction that ends, you'll see SMAR run to free up the storage. And as a matter of fact, has anyone ever looked at a storage violation? If you've looked at a storage violation, what program is running at the time of a storage violation? Well, if you look at trace, you'll see it's SMAR. SMAR will call storage manager to free the storage. Storage manager goes, uh-oh, I have a storage check fail, and boom, that's when the storage violation occurs. Yeah? So it's actually driven by this domain gate call that's actually issued by the transaction manager. So there is an order to things, but nonetheless, once you start to see them inside of trace, you learn about it, you see that it works exactly the same way no matter who's running. And that's what helps you remember it. Okay? Now, I will point out that the S2GF, that's how IBM references storage above the bar. They decided they're going to make a copy of all the programs that already exist with SM, and they'll call it S2 to identify the differences between above the bar and below the bar. So, I'm told, and I believe it's true, the first two characters identify who owns that program. So right away, if you see a failure in DFH SM something or another, you know you're in Storage Manager. The problem is in Storage Manager because that is a Storage Manager program. That's what it boils down to. The last two characters are supposed to give you an idea of what it's doing, and of course you can look them up. So we refer to something like SMGF as Storage Manager Get Main Free Main. The physical program, you put a DFH in the front, and it does exist. There is a program called DFH SMGF. If you go to row 2, which is Storage Manager, column 10 in the domain gate table, and you follow that address, you'll see a header on the top of the module that says DFH SMGF. You can chain up to every module within CICS. Right? So that's part of what you can do in terms of debugging. Now, I didn't talk about these guys yet at the bottom, but I will in just a second. So, any individual gate can provide many functions. Storage Manager Get Main Free Main obviously does both Get Main and Free Main, right? So there could be several different functions that it actually does. And then we started to talk about generic gates. When you look at the domain gate table, the real domain gates, what's a gate? It's really just a program, right? It's a program that takes a COM area, it's called a parameter list. But nonetheless, you call the program with a parameter list, it does some functions, and it returns some data. Well, that starts at column 10 in the domain gate table. What about all the earlier columns in the domain gate table? Those are reserved for something called generic or callback gates. And it works a little differently. Think of it as IBM creating a methodology for broadcast functionality. Good examples of which? Statistics. Statistics actually doesn't own a row in the domain gate table, it owns a column. Every domain is a row. So what IBM decided was inside this table, what they'll do is they'll say, oh, okay, you know what, we'll give statistics row 4, a column 4. And if you're a domain and you want to support statistics as a function, all you have to do is put an address of a program for us to call when we do our statistics call. And we'll drive that program, and it'll put out its stats. So it's a way to provide generic function. It's brilliant when you think about it. If I'm a domain that wants statistics, I put a program that you should call. If I don't want to support statistics, I leave it out. And we'll talk about leaving it out in just a second. And that's how a broadcast function call works. So think about it. How often do you run statistics? Well, you guys set that up. You decide how often, right? You run the 3-hour, it used to be 3-hour intervals, now the default is every hour, right? So you choose whether or not you run things like monitoring and statistics and so on, right? Those are generic functions. There's only a few of them, 7 or 8 of them. There's statistics, there's exit calls within the AP domain, or one of my favorites, DMDM. That is the name of that column, but everybody has their own program. You'll see there's an SMDM, an APDM, yeah? And what's actually happening is this is the gate that brings CICS up. It's column 2. inside the domain gate table. And what happens is when Cics starts up, who really starts? It's the kernel. He's the guy who gets control. DFH-SIP gives control to the kernel. And what does the kernel do? He starts every domain at the same time. We call it that horse race startup is what they call it, right? But what he really does is he goes down column 2 in the domain gate table and he says, run, 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 run. And then they all run independently, asking for time and doing other things, right? And then eventually Cics comes up because they've all initialized. So everybody supports the DM gate except the kernel. See, he's the guy who starts it, so it wouldn't make sense, right? So he's the only one who doesn't have a program in that slot, but everybody else supports domain management. There's a broadcast message, bring everybody up. And that's kind of how it works. Right? In fact, if you look at a system dump, and you go ahead and you print off DM equal 1, which is the summary in a system dump, DM equal 2 is detail, you'll actually see he has a list of every single domain and whether or not they've come up. And if you take a dump during shutdown, whether they've come down or not, right? So every domain tracks what it does. What does the domain manager do? He handles startup and shutdown, end of story, right? He knows exactly what they've done. So he's one of the generic gates. Now, you can use diagnosis reference. Like I said, use it as a reference guide. Otherwise, you'll be totally turned off and never use it. Yeah, it could be horrible to read. It's 2,000 pages. Anyway, let's show you a little bit more under the covers. So I've already mentioned the name of the program is DFH, the 4-character domain name, and then that's the program. But do you think developers within Hersley sit down there and write calls like that? No, they don't. IBM provides macros, assembler macros. In fact, there's a DFH, SMGF, M macro. And if I want to get main and I'm a domain developer running in the AP domain and I need 100 bytes of storage, I'm going to code a DFH SMGF M gate. And then I'm going to pass it some parameters. Maybe I want to do a get main or a free main. How much storage do I want, right? So I'm going to pass a bunch of input parameters, and as part of the response, I expect to know if I got it or not, and what's the address of the storage area I got. So there's a typical example of what a domain developer might do. Just to take it one step further, if you're really interested in internals, there's 2 other DFH SMGF thingies. Yeah? One is called DFH SMGF Y. If you've written any exits, you'd know that Y is a limited form of the M macro. Like if you're writing an exit, you can't always do the exec CICS commands in an exit. You don't have access to the exec API. But you need a piece of storage, what do? So IBM lets you use some of their macros within an exit, but they let you use the DFH SMGF X macros for the XPI. And if you want to know what parameters to set, there's a copybook called DFH SMGF Y. So the Y copybook would show you how the X macro works and how the M macro works as well, yeah. And so that's how you could learn about what the parameters are. But nonetheless, you pass it input parameters, you get output parameters, right? With responses and reason codes. So there's a typical example, right? XMAT is the transaction manager attach function. Everybody goes through that to get a task attached to Cics. And one of the first things he does is gets a piece of storage, right? So he calls SMGF. Now, it's not drawn here, but before we get from here to here, we go through the kernel. We're going to see the kernel keeps a stack of everything that's going on. And so somebody issued that SMGFM call, and it ended up in SMGF within Storage Manager. So, just to highlight what you might read in diagnosis reference, those are specific functions. Get main free main, that's a specific function. Obviously, it's owned by the first 2 characters, i.e. SM. Yeah? That's a specific gate. Right? And we've done a few of them. Here's another example. DS, dispatcher, SR, suspend, resume. If you ask for something and it's not available, like you do a read of a file and somebody has to do an MVS IO, you'll get suspended, right? In fact, you'll end up suspending yourself, realizing you don't have the data, right? So the last thing you'll see is a DSSR pop task, because you're now off the QR TCP and the QR can run somebody else, right? And so that's just another example of a specific gate. What about a generic gate? Well, we mentioned a few of them, right? We talked about DMDM, we talked about STST. They're specific generic gates because they provide function to many domains. It's actually owned by the statistics domain as a gate. But interestingly enough, the statistics domain doesn't write any programs for it. Everybody else writes a program that wants to participate in that function, okay? So, again, I mentioned these examples a little earlier. There is one other twisted thing called a callback or a reciprocal gate. There's only one of these, so it doesn't, two of these, so there's only a couple of examples of them, but it's a really interesting concept. Think about this, right? When a user hits enter at a terminal and a task starts up, right? Who's actually running at the time? Well, in the case of somebody hitting enter at a terminal, it would be terminal control processing his input requests, right? So terminal control is running. He's processing an input request. He puts a TCTTE on a chain that he's going to process and read the data and start a task up. But who handles start of task? Well, it turns out the transaction manager is going to schedule a task for its first dispatch. So the transaction manager talks to the dispatcher. But we got a problem. We haven't made it through the kernel yet. The kernel is what provides, or who provides, stack storage for the user to run. What is stack storage? When we think of stack storage, if you're an old-time regular programmer, if program A is running, you don't have a stack. Why? Because program A is running, life is good. But if A links to B, then you're running B, but you have to remember the details of A because you want to come back to A, right? And so you stack A. When B links to C, now you got A and B on the stack. B is the most current element on the stack. And when you return, you go back to B. And when you return, you go back to A. So we need to keep some details about programs we intend to come back to. That's what we use a stack for. Internally, within Cics, it's slightly different. IBM came to the conclusion, rightly so if you ask me, that everything lives on the stack. So if A is running, you already have a stack and A is on it. If A links to B, one domain to another, then A is on the stack and B is on the stack, and that's where you're running from. The working storage from B actually lives in the stack section. So it's very convenient the way they built it, right? The point is if a task starts up and it hasn't been dispatched yet, there's a two-step process to get a task running in CICS. One is task attach, and then there's first dispatch. If we attach a task, it means we tell the dispatcher at some point you have to give him control because we want to run it, right? But at the same time, he's never run, so he has no storage. So the solution to the problem is we got to call the kernel. But you can't call the kernel, because if you called the kernel, you already need a stack. It's a chicken and egg problem, isn't it? Right? I want to call the kernel to get him a stack, but wait a minute, to call the kernel, I have to have a stack. So IBM invented a gate that does a transfer of control. Basically, the dispatcher transfers control to the kernel. The kernel gets the stack, and then he does a DSKE task reply. And that's why the very first thing on a kernel stack you will see is the kernel, if you look at stack storage. And the very first trace entry you'll ever see for a task starting up is a DSKE task reply. That's why. Okay? That's called the callback gate. There's also examples in the recovery manager for callback gates. Now, let's talk about the domain call format. What you're going to learn is to do a lot of internals. Trace is probably the best element you can work with. And everything you're going to see that I show you here about domain gate calls, that's what trace actually is. It's telling you what's going on within the domain gate calls. A stack entry has 2 bytes in length, 2 bytes of binary zeros. Anyone remember what that's called? Anyone remember the term LLBB? Yeah? That's how we have a variable length control block. We put the length in the first 4 bytes, but since the lengths are never going to be bigger than 32K, we'll just use 2 bytes and reserve the rest and never use it again. And then you get the format, the version number of the domain gate call. That's how IBM can do this automatic delivery. What do they call it now? The continuous delivery, right? Because all we have to do is give it a different format or version number, and you can have the same program running multiple times. Now, this is a variable length control block. So it has 8 bytes of existence bits. You flip the bit on, it means we're passing the parameter. If the bit is off, you're not passing the parameter. And for example, the first four parameters are always the same. There's always a 1-byte function, like get main or free main. There's 1 byte reserved, who knows why. Then a 1-byte response and reason code. So if you just do 1, 0, 1, 1, that means if you look at the existence bits in hex, it's always a B. 1, 1, 0, 1, 0, 1, 1. Yeah? And that's the way it looks. All the rest of the parameters up to 64, because they don't feel they need more than that, are all variable. So let's show you an example. So, yes, any module calling a domain, we talked about this. Okay. So, the formats are owned by the domains. I give you an example. Dispatcher owns the format for change mode. This is all really nice. We talked, okay, for example, statistics domains owns the format for the generic gates, and we talked about generic gates. Let's show you this parameter list in action, because it's exciting. So, just as a reminder, right? Domain A. Well, if we're starting at the beginning of time, it's always the kernel. When he calls domain B, the stack adds B to it. But A was already there. So I told you about that nuance, where the stack always has information. And then, what we're saying is if AP domain calls storage manager, we always go through the kernel. What does the kernel do? Add another piece of stack storage. What's in the stack storage? There's a fixed piece that has registers and other things. There's a variable piece. What's in that variable piece? That variable piece is the working storage section for the module you just called. So, you know, when you send a dump to IBM and they say, oh, you know, I need more information. I need another dump from you because I don't have what I need to solve the problem. I always laugh. See, they don't want me on the other end of the phone because I just laugh at them. I'm going, okay, yeah, you're busy. You can't get to me right away. So you're just asking me to produce more information that's probably useless in nature so that you can blow me off for a week. I got you, no problem. And then they get all quiet, yeah? And they usually get better response that way. The reason I'm saying this is if a failure occurs, they know what program's running. They got the working storage for the program. They may or may not have trace, but they don't really need it. They know exactly what's going on. Exactly. And so do you. So, you know, when they say, oh, well, we don't know where the problem is, and I say, well, it's offset at 21 Charlie in Storage Manager, SMGF, and all of a sudden there's dead silence on the phone, because then they know you can actually tell them this, because it's true, yeah? Anyway, so we're going to see he provides consistent linkage for recovery. Application programs have no external interface to the kernel. That's fine. Associated trace entries are dumped. That's what we're going to do next. And the kernel domain returns response codes from a call to the caller, and we'll show you how that's done. So I put in a bunch of notes in case you read it later, because it is internals, and you're not going to remember anything I said. So anyway, or at least not all of it. So call. Right? So a call is made by the kernel linkage, so you realize you always get control from kernel linkage. You don't get control from the actual module. And by the way, return is always to the kernel linkage. So think about it. AP calls storage manager. AP calls SM. Not really. AP calls kernel. Kernel says, oh, let me look up the address in the domain gate table of the module I need to give control of. Oh, it's SMGF, row 2, column 10, yeah? I'm going to give control to that module. And now I'm running storage manager. So you went through the kernel on the way in, so the kernel knows exactly where you are. And then I'm going to go back through the kernel, because when I do a BR14, who called me? The kernel, so he gets control. He says, oh, I've got to load that other guy's registers and do a BR14 back to him. And so everything goes through the kernel. So this is an example of a parameter list taken out of DFH DSSRY, which is available to you in MacLib, I believe. And you could easily see down here the existence bits, right? Again, you'd have to be an assembler kind of guy. But there's that 1 byte of existence bits. You'll notice the 80-bit is available, but not the 40-bit. So that's how you get 1011. The 40-bit doesn't exist in the first nibble, right? But then you have all these parameters are variable. So you can actually figure out what parameters are passed on each call into a particular module in Cics. And then on response, you can actually see the function, response, and reason codes. Now, you're probably saying, Ezriel, I'd rather have a drink than do this. Come on. Well, one of the things I'll show you is it's not quite as bad. You can get to this level if you want to, but there is a higher level that you can support if you have a bit of trace, which, by the way, for those people who say they don't have trace, yes, you do, because you can't turn off exception trace. So if you get an exception, it is in trace, and you'll have this information. Now, this I find very interesting. Couple of points to point out here. What is a good return code from one domain call to another? Hex 01. You're going, what? What's a good return code from a Cics call? Hex 00. Internally, IBM doesn't use hex 00 anymore. Why? Because they want to be able to figure out whether they ran the function or not. If they initialize it to 00 and they're looking at 00, is it a good return code or did we never make it there? So they decided under the covers, 01 is good, right? It means you've done something. Now, notice an OK response, I don't expect a reason code to be set. Makes sense. And then you get those various worse errors. Exception, something went wrong. Disaster, doesn't sound good. Invalid parameter list. Well, since it's one domain compiled and issuing calls into another, the only way you're going to get an invalid parameter list, if you ask me, is with a storage violation. So that's pretty bad. Storage violation within the system is probably ugly. So that's pretty serious as well, and you can see the parameter list is set. But then you go down to 05 and you're going, wait a minute here. It says it's a kernel error. You don't even set the reason code. What the heck is going on? Well, now I have to tell you another efficiency within IBM's coding for this linkage. When you look at the domain gate table, and you look at a particular domain that only has 2 programs, the domain gate table can hold 58 programs in a row, something like that. So what do we do with all the columns that we don't want to put any programs in? The answer is IBM said, we don't want to put binary zeros because if you take a bad branch, the entire region will blow up, right? So what they did was they invented a program called DFH-KE-RKE. It's the kernel error routine. What they do is they initialize the row of the domain gate table with this module in every slot. Then as a domain comes up, he replaces that module with the real program. Whatever's left is not valid. But if that routine were to get control, what does it do? Returns a hex 05 kernel error. So why doesn't it set the reason code? Because it's used in several different functions. Sometimes IBM says there's a function within Cics, right? But we're not going to make it available. You know, there's sit parameters you can turn on. You ever turn on TCP/IP, right? If you say no, and you bring up a region, can you go into CEMT and make it yes? No. You have to bring up the region with that function. Then you can make it no or yes. So there are things that you can do within Cics that don't allow the function to be created. If that's the case, and you try and run the function, the program's not there, it gets a kernel error. That's not a serious error. He handles it under the covers and he says function not available. There are other things that if a kernel error came back, it would be a serious error. You want to have a little fun? Oh, I'm on tape. I shouldn't say this, but I will anyway. Yeah. I'll tell you anyway. You want to have a little fun? Row 2, column 10 is the address of storage manager get main free main. Chances are, if you look at a domain gate table, you'll see this repeating address. When you see the same address repeating 5 or 6 times, you know it's the kernel error routine because most of the table looks like that, right? If you zap that address into storage manager get main free main, region will come down lickety-split, faster than you can blink, yeah? Because somebody does a get main, and he just says function not available, and Cics goes, oh my God, and falls over dead, yeah? So it's an example to show you that, yes, it could be a serious error, or it may not be a serious error. But we don't know. It depends on what function is not available. And that's how it works under the covers. Now, my favorite one, purged. Why do they have a separate thing for purge? Because whether we like it or not, as systems programmers, we've been killing tasks for years. We had purge, didn't always work, so they gave us force purge, didn't always work, so they gave us kill, murder. I know what's coming next, right? But we literally, everybody loves to kill it. It feels good to just get it out. Ooh, it's a problem, kill. Ooh, yeah. So the point is just imagine you're growing this stack. You're 16 levels down, and you decide to kill that task. If we didn't have a way to tell everyone who called you that we've just been killed so they can clean up properly, the system wouldn't function anymore. And so that's why you'd see an 06 purged. Now, I'll show you how these things show up in just a second. So finally, you'd see things like this as input parameters to DSSR, and you'd see this as output parameters for DSSR. But let's show you an example. So, we got the function, response, reason code. These fields are not 1 bit. It's the existence bit that's 1 bit. Each of these fields are as big as they need to be, but they're all put in at the end. So obviously there's a way that IBM knows how big each of the fields are, right, if they're truly being passed. So here's an example of DSSR. But this is what you get. Now, I'm sorry for those that don't like trace, because I know it looks ugly, but it's really, really important to learn a little bit of trace, whether you use it on a daily basis or not. What's nice is this is a new style trace entry. This will give you some information. And again, what comes out in trace? If you look for full trace versus abbreviated or short trace, you always get this 1 dash, 2 dash, 3 dash, right? Those are control blocks coming back within trace, okay? If you look at full trace and you get a 1 dash, guaranteed that is always the parameter list. So if he ever returns a parameter list, the 1 dash is always the parameter list. Now you could recognize it. There's the 2-byte length 70, and sure enough, this is hex 70 in length, right? Now, if you remember where the existence bits live, well, there's version 1, format 14. B, remember I said it always starts with a B, right? Function, response, and reason code. Now, you'll notice this is exit, so this is on return. Entry is on entry. So my response and reason code should be set on return. Now, how many other parameters are there? Well, let's see. We got a 1 and a 1, so there's 2 parameters. Then we got a Charlie. A Charlie is a 1, 1, so there's another 2 parameters. Now we're up to 4. Then there's a 2, which is just 1 more parameter, 1 2-bit, right? And then a 40-bit. 1 more, there you go. 6 parameters were sent. That's it. Now, before you say, oh, shoot, I don't know how to go in and look at all this, let's see how many parameters there were. Oh, we didn't give you the entry for this. On entry, you would have seen the parameters, right? But we know that there's 6 parameters, right? We know out of the 6 parameters, 1, 2, 3. Well, we know the response and reason code. One of them is the function. Oh, we did highlight it for you, so I did look it up. Take it back. Here it is. So there's the corresponding analysis. I don't know that I'd go into all this trouble. Like, for example, on a function, wait old W is kind of a boring one. That's what terminal control goes to sleep on. And what he's showing you over here is you can actually see things like when he exits await, it's a TCP underscore norm. So he's kind of showing you the function was wait old W, and he actually woke up because it was a normal TCP underscore norm. So it was just part of his cycle to wake up. The point that we're getting at here is you can actually look up what each individual field means and what it says. I wouldn't necessarily have used this particular trace, even though I did, but you'll see on other pieces of trace there are times, like storage manager is notorious. Storage manager, if you count the number of parameters that normally go in, you always look at it and there's always one missing, right? The one that's missing is the actual subpool that it came out of, but when you look in here, you could see the subpool name. Yeah. The point is that I'm getting at is you don't have to look at the bits and go out and get this control block function. Normally, it will be here in the response of full trace. So most of it you'll get. On occasion, you might have to look one up, so don't get nervous. This is just how it kind of works, right? But you could look up everything as we did, yeah? This is a reserved field. The response is DSSR underscore OK. Everything was good. The function was a wait old W, but you'd have to know all about the dispatcher and so on. Okay. So now let's talk about some core control blocks. Does everybody kind of know the difference between a transaction and a task? Maybe? Okay. So a task is the minimal piece of work within CICS that runs. Everything is a task. The only thing that allows you to become a transaction is you have what's called a transaction environment. right? In order to have a transaction environment and i.e. be able to run exec CICS commands, you have to go through the transaction manager. So we'll learn out of those 4 domains I talked about, AP, DS, KE, and XM. We have some system tasks. Yeah, I might run a few minutes over. We have some system tasks that only go through the kernel and the dispatcher. They can't issue any exec CICS commands. They're meant for the system. Our stuff is all initiated via AP, goes through XM, goes through the dispatcher, goes through the kernel, right? So when we look at a particular unit of work in Cics, you might see something that looks like this. Some guy types in a 4-character tran ID, hits enter, gets a screen. He fills out the screen, hits enter, and gets a response back. In reality, under the covers, we actually have to run multiple tasks because we're pseudo-conversational. So actually, a piece of work in Cics is usually made up of multiple individual tasks. And that's why when you talk to large companies, they go, yeah, we run 100 million transactions a day. Well, no, they don't. They run 100 million tasks a day because that's all they can record. How much business functionality do they run? It's usually about 1/3. Yeah, that's the average. So when a guy says, I run 1 million transactions an hour, it's probably 300,000, right? But these are all individual tasks, which mean, first of all, you could look at them individually, even though a combination of many of them make up a business function. And like we're saying over here, the kernel has to know about you, the dispatcher, and the transaction manager. So, a Cics task only will have the dispatcher and the kernel. A transaction environment will allow you to have the exec CICS API structure, which allows you to issue Cics calls. So, the very first control block we're going to do is called the kernel task. First of all, every domain has at least one major control block, but it depends what they do for a living. The kernel spends his time managing tasks in the system, and the way he does this is he has a control block called the kernel task. That's what he does. Yeah? And so everything associated with a transaction is held off of the kernel task. Now, I don't mention it on this page, but the other thing he manages is TCBs. So he has another control block called the KE-TCB that is hung off of a different chain, and that's how he manages TCBs. From an application point of view, from a transactional point of view, we're interested in kernel tasks. Now, what is a kernel task? It'll contain append information associated with a transaction, should it be appending. It'll have the registers and PSW, and all that's contained within the stack entries. And the stack entries are chained off of the kernel task. And if you go through IPCS and you type in K=1 to summarize it, you'll actually see the stack storage associated with the individual tasks. So the kernel is very important because any failure occurs, first failure data capture occurs in the kernel. We'll know exactly where you failed. And by looking at a piece of stack storage, he'll actually tell you what went wrong to some extent. Okay? So that's why the kernel task in the kernel is important. The dispatcher is something completely different. The dispatcher decides who runs and when he runs. Right? He has a bunch of algorithms that he figures out. Is it a high priority, low priority task, right? Is there something more important in the system that needs to run? And oh, by the way, if we have multiple TCBs, he has a list of tasks that want to run on each of the TCBs, and he dispatches them based on a priority order. So why would you be interested in looking at the dispatcher in a dump? The answer is, if you have any waits or hangs, who's going to know about it? The dispatcher is the guy that's holding you up. So we're going to find out the dispatcher has something called a DS_task or a DTA under the covers. And it'll tell you your priority. If you're waiting for something, he'll tell you what you're waiting on. He'll give you a suspend resource name and type, and all you have to do is search. I used to say go into diagnosis reference or problem determination. Now I just say Google it. Right? And somebody will tell you. It used to be only internally within Cics, but now vendors use this as well. And so you could learn why you're held up, right? But again, you can troubleshoot that way. The transaction manager used to be part of the AP domain. They split it up and made it separate, right? And it represents a transaction in Cics. He is a true manager. He doesn't do anything himself, but he assigns all the work. And what I mean by that is he has pointers into all the different domains that he needs to call to build a transaction. He has a pointer into storage manager. He has a pointer into recovery manager, right? He has a pointer into the AP domain. He has a pointer into the transaction, the security domain, right, to make sure. And what he does is when transaction manager gets control, because the dispatcher tells the transaction manager, okay, we're going to run the guy, he has to talk to all these different domains, set up the entire environment, and then he gives control to the AP domain to run your program, okay? So that's kind of what happens. So he's a guy you can go to if you run into a situation where you're looking for example, file control. You did a read of a record on a file, right? You wouldn't necessarily, you could look in file control and he'd tell you that the file's in use, but he wouldn't tell you who was using it. That is chained off of the XMTXN control block, yeah? Because if you're in file control, it's managed here for recovery purposes. Now, one other thing I'll mention is he manages max task and tran class, so that's his other function. If you're in a situation where the region's at max task, this is the guy who could tell you why. If you're hitting a tran class limit in a particular tran class, this is the guy who could tell you why. And again, he has pointers into the program manager domain, the AP domain, the recovery manager. There's about 8 different domains he talks to. Okay. Now, storage manager. It's obvious, he supplies storage to and from transactions, right? He handles things above the bar, below the bar, which is above the line, and below the line, right? And again, storage manager, why is he important? Well, a lot of the problems we still have in Cics is all about storage management, storage violations, right? We don't have a lot of protection in place, even though we claim we have tran ISO and subsystem storage protection and all these features. You can still get a storage violation, yeah. Because nobody will ever stop you from shooting yourself in the foot, right? If you have a COM area, it's 100 bytes, and you write 150 to it, you will get a storage violation, yeah? And so at the end of the day, storage manager is a useful place to go to for storage violations, looping tasks that exhaust storage, or what we used to call short on storage conditions, right? And this is the guy to go to look at. And today, if you look in a dump at storage manager, he'll tell you which DSA has the violation or which DSA is eating up all your storage. So they make it very easy. Okay? And then just a point of fact, obviously we started using 64-bit storage. You have to be at a certain level of ZOS to actually get 64-bit storage. But today, for example, temp storage is above the bar. The trace table is above the bar. And so we bought back a lot of room below the bar to be able to run physical work. So if you've had a region that was like maxed out, you could probably put, I would guess, somewhere in the area of 30% more work in there today. Now, and so I just go through a little bit about A-mode 64 is about 8 billion times our 2 gig region. It's 16 hexabytes. Yeah, okay. Now, I'll give you some of the changes. 4.2 is when they started using 64-bit, right? The anchor blocks moved above the bar, and IBM is moving all the control blocks above the bar. Now, why am I pointing this out to you? Because if you've been in internals for many years, or you know how to look at some internals, and you go back and you say, the address of X is at this position, you go there and going, holy cow, it's all zeros. Did they move it? You have to get your brain around an address is no longer in a 4-byte area, but an 8-byte area. Once you get that into your head, things start to get better. Because they haven't necessarily moved everything above the bar, but they now hold 8 bytes for the address no matter what. Because the assumption is eventually it'll move above the bar. So if you ever go to an address area and it looks like really small, like E6 or it's all zeros, then you got to look at the one next to it and assume either it's 64-bit or it's a 31-bit storage area and the first 4 bytes are 0. So the last little bit is the AP domain. It still runs most of the function. All the exec CICS commands and the interface itself is within the AP domain. It makes it easy to add function, right? And so you could see a lot of domain gate calls in here. In fact, it's so large that at CICS version, let's go 4 and older, there was actually 2 rows in the domain gate table to support it, row 16 and row 18. In 5.4 of CICS, row 16, row 17, and row 18 all belong to the AP domain. So they actually want more rows because they have to have more programs in there and they need room for it. So it just goes to show you all the function that it runs. Other things within here, BMS if you're still using it, the command interpreter, event capture. Events are fairly new. Doesn't matter. They put it in here. It was easy, yeah? Distributed transaction processing and some of the other old stuff live in here. No, IP doesn't live in here. IPIC has its own domain, right? Because it's a newer function. Dynamic allocation, your sign-on, sign-off program, CEMT, CETA is all within the AP domain. And again, I don't anticipate it'll move anytime shortly, but it might, yeah? File control is still in here, it's not its own domain. Interval control is still in here, so it's not its own domain. So things that they're not really looking to architect into their own domains still live here. So don't get me wrong, transient data today in CICS version 5.3 and higher is fully thread safe. And if you look at a system dump, it'll give you a summary and a detail, even though it's not a domain. If it's not a domain and you're looking in a system dump, it's always 3 characters. So it'd be transient data would be TD, add a P at the end. File control, instead of FC, it would be FCP. Interval control, ICP. But that's the only difference as far as you're concerned. It seems to work like a domain anyway, yeah? And then you can see some other stuff. Backout is still done within here. Abnormal condition programs, key pointing, node error. So there's a lot of stuff that still runs in AP domain. But I'd say today it's less than 50% of the problem, probably even less than 40% of the product. Now, in terms of physical code, if you looked at all the lines of code, in terms of what's driven within Cics, this is still the majority. So this would still be 60 to 70%. Every Cics call, right? That's what we do. Yeah? Okay. So, just hopefully that gave you an idea of how the internal functions of Cics work and the basics to see a transaction starting up. Your homework assignment, should you choose, is to go out there and turn on trace, right, auxiliary trace in a simple test region, run a transaction from start to finish, find out where it starts, find out where it ends, and then take a look at the programs that get called. The 2 characters that start them, like DSKE or XMTA, XM is transaction manager, look up DFH XMTA and do a little research and you could see a task start and end, and that will start to show you the whole picture for internals. Remember, it does take 2 weeks to teach you this, so I'm hoping you got a little bit out of that. So, any questions? No, it's lunch. Why would there be any questions?
We can take some questions offline.
Yeah, absolutely. You come see me. I'm here. Thank you.